Okay, next I would like to talk about what happens to certain objects when we do an inversion. So I have a circle with center O. I've hidden the circle, but I have a circle with center O and some radius R. If we could see the circle, we could measure R. And I have this line XP. X and P are chosen in a certain way, but I have this line, which is just some line that doesn't go through the center of inversion. Turns out we have a theorem that says that if I map all the points on that line by inversion, they're going to go to a circle. I can't get the entire circle because I can't run x off to infinity on the screen here. But if I could, remember infinity would go to O and this whole thing would close up. So this line under inversion around the circle with center O actually goes to a circle that passes through point O. So if the line doesn't pass through O, it'll be mapped to a circle that passes through O. Here's the outline of the proof of that. So all we have at first is O, the circle with the center radius R at O, and then we have this line which we see here as XP. So how did we get X and P? P is very important. P is chosen so that this line is perpendicular. Given this line and O, we can construct the perpendicular and then find P as the intersection. X is just an arbitrary point on that line. For each of those, we can apply the inversion and get P prime and X prime. Then we know from a previous theorem that the triangle OPX, which is a right triangle, is similar to triangle OX prime P prime. Remember, the X and the P get shuffled there in the similarity. So the angle at P matches the angle at X prime. We know that's a right angle, and we had a previous theorem a while back that right angles can be inscribed in circles, in semicircles actually. So the triangle OX prime P prime is inscribed in the circle with diameter OP. And again, if I move X, there it is. A couple of other details. The point at infinity would get mapped to O, and O would get mapped to the point at infinity. But we're talking about the line, where the points on the line go. So every point on the line goes to one of these, and the point at infinity goes to O. And it takes a little bit of work to show it, but this mapping is one-to-one and onto. Okay, it is onto, and we'll give you the complete circle. The corollary to that, which would come from the same argument in the same picture, we see in this picture, remember, P goes to P prime, but P prime also goes to P. Okay, points are inverses of each other, so the little blue circle I'm forming would get mapped to the line. So circles that contain O get mapped to lines, and lines that don't contain O get mapped to circles that do. Okay, here's another picture for another theorem. What about circles that don't contain O? So we said circles that contain O go to lines. Turns out circles that don't contain O go to other circles. So let's walk through the outline of that. So we have this circle. We have O, which is the center of inversion. We have some unknown circle that I've hidden here, but it has a given radius. And we have this circle out here with this center that doesn't go through O. The circle doesn't go through O. I can draw the line from O through that circle and find the two intersections Q and R. I can let X be any point on that circle, and then we can find the inversions of everything. At this point, I can go ahead and drag X and see what happens when we move X around. So look at that. The image of the black circle is the blue circle when we let X go around under inversion. Okay. Just an outline of the proof, not all the full details, but we know that the triangle OQX is similar to triangle OX prime Q prime, and ORX is similar to OX prime R prime if we shuffle the points. So we can use that and the fact, similar to what we talked about a minute ago, if you have a triangle inscribed, this is that inscribed, that angle is half of the 180 degree angle. This is a right triangle. Okay. We can use that. We know some angles about these littler triangles. Let me get rid of the image. So we know some of the angles in here, and we can show that angle R prime. Again, this isn't direct because it's a different triangle than one we were talking about, but with a little bit of work we can show that angle R prime, X prime, Q prime is equal to 90 degrees, which shows us when we move that around, that's for an arbitrary X where X prime goes. These little triangles are inscribed in the circle that we see when we actually do it. So this is a right triangle. We can show that this is a right triangle, which will be inside of a circle when we move it around.